Alright, so today we're going to be talking about graphing logarithmic functions with dilations, so either vertical stretches or vertical compressions. If you think back to other functions that we've done, remember this is when we're multiplying our function by a number a. And depending on whether a is greater than 1 or less than 1 but greater than 0, we'll either have a vertical stretch or a vertical compression. And we can see that in this chart below. I want to go over some examples, but feel free to pause the video at any time. I encourage you to fill out your document as we go through the examples together. That way it'll make more sense, I think. But feel free to go at your own pace. Okay, for example 1, we have f of x equals 2 times log base 4 of x. The first step that we want to take is to identify the dilation on this function. If you notice, we have a 2 being multiplied, so a is greater than 0, that means we're going to have, greater than 1, that means we're going to have a vertical stretch. And this is the only transformation that we have on this graph. So next we want to graph our parent function. In this case, our parent function is f of x equals log base 4 of x. And remember, for every parent function, we want to include the 3 key points. Those key points are 1 over b, comma, negative 1, 1, comma, 0, and b, comma, positive 1. And b in this case is going to be your base. So for this particular problem, our base is 4, so we'll fill in that chart replacing b with 4. We want to include our vertical asymptote on the graph, and remember, as always, the parent function has the vertical asymptote of the y-axis, or in other words, x equals 0. So go ahead and put that on the graph as a dotted line. Now we want to use that table to put the points of our parent function on the graph. Again, we will be dealing with small fractions, so graphing might be difficult, but just do your best and make it as neat as possible. Once you've plotted the points, go ahead and connect those dots. And remember, our vertical asymptote, that is a line that our graph will not cross. It'll get really, really close to it, but it will not cross that line, x equals 0. So now that we have our parent function graphed, we want to get into graphing our transformed function, so the function that has the vertical stretch. So what we want to do is we want to initially start with that same table of values from our parent function. So 1/4, comma, -1, 1, comma, 0, and 4, comma, 1. And then in order to apply that vertical stretch, we're going to take all of our y values and multiply them by a. In this case, remember, a is equal to 2. So our x values are going to stay the same. We're still going to have 1/4, 1, and 4, but we're going to multiply our y values by 2. So that's going to give us -2, 0, and +2. So we have a chart for our transformed function. Since we haven't done any transformations on our x values, our vertical asymptote is going to stay the same, and that's going to be x equals 0 again. So let's go ahead and graph those 3 points for our transformed function on the graph below. And once those points are on the graph, connect the dots as best you can and put in your x or your vertical asymptote. Okay, now that we have our transformed function on the graph, we want to talk about the domain, range, and asymptote. We've already said that the vertical asymptote is x equals 0, and remember that's just the y-axis. For our domain, we're looking for all of the valid inputs for our function. So in other words, all of the x values that we can put into the function and get something out. So if you look at the graph, notice that all of the x values in our function are greater than our asymptote. And remember, because it's an asymptote, our graph is not going to touch that line x equals 0. So for the domain, we're going to take all x values greater than but not equal to 0. For the range, we're looking for all of the outputs of our function. So in other words, all of the y values that are included in our function. If you look at the graph, both ends of our line continue on forever. So that means that our range is going to be all real numbers. So if you compare our second graph to our first graph, you can see that it is stretched a little bit, which is what we expected by multiplying that function by 2. We expected a vertical stretch. So let's try another example. This time I want to combine a vertical dilation In this case, it's a vertical compression and a horizontal shift. Our first transformation, we have a 1/5 being multiplied to the outside of our function. So this is going to give us a vertical compression because a is greater than 0 but less than 1. Our second transformation that we have on this function, we are subtracting 2 on the inside of the parentheses. So that means we're going to have a horizontal shift to the right 2 units. Okay, now we want to graph our parent function. Our parent function for this problem is going to be f of x equals log base 3 of x, because our base is 3 in the original question. And we want to go ahead and make that chart with the 3 key points, 1 over b comma negative 1, 1 comma 0, and b comma positive 1. So we're going to replace the b with 3 in each of those, giving us the points 1/3 comma negative 1, 1 comma 0, and 3 comma 1. And as always, our vertical asymptote for the parent function is x equals 0. So let's draw in that vertical asymptote as a dotted line. And then we want to put the 3 key points from our table onto the coordinate plane. Once the points are on your graph, go ahead and connect the dots as best you can, making it as neat as possible. Be sure to not let your line cross that asymptote. Again, pause the video at any time if you need to slow down. So for step 3, we want to find the new coordinates so that we can graph our transformed function. But we first want to start with the original coordinates from our parent function. So I've just copied that chart below. And I'm going to rewrite our transform function just so we don't have to keep scrolling back up. It's f of x equals 1/5 times log base 3 of x minus 2. So when you're applying these transformations, you want to think in terms of your order of operations. So you see that we have x minus 2 in parentheses. That means you're going to add 2 to your y values first. To your x values first. That's going to be the first thing you do. And remember, we're adding 2 because when it's in parentheses, we take the opposite sign. So now I'm just going to create a chart with 2 added to each of those x values. When we add 2 to our x values, we get 7/3, 3, and 5. And we're going to keep our y values the same for this step. In order to incorporate our second transformation, we're going to multiply each of our y values from our new orange chart by 1/5. And we're going to do this after we've already added 2 to the x values. So this is our second step in creating our chart for the new transformed function. The new y values that we're going to have are going to be -1/5, 0, and +1/5. So remember, when we are looking to find our vertical asymptote in a function that is not our parent function, remember that the vertical asymptote is equal to -h. So in this particular problem, our h is -2. That makes our vertical asymptote equal to x equals +2. So go ahead and put that on your graph as a dotted line. And now we're using the points from our pink table to plot the new transformed graph. Now that we have all 3 points on the graph, connect the dots as best as possible. And make sure the bottom of your graph is not crossing the vertical asymptote. You'll notice that the curve of this graph is a bit sharper than the ones that we've seen, and that is a result of the fact that we vertically compressed our graph. So now let's take a look at the domain and the range. Remember, your domain is going to be all of the x values. So looking at our graph, all of our x values are greater than our vertical asymptote, and our vertical asymptote occurs at x equals 2. So our domain is going to be x is greater than 2. For our range, there are still no y values that are not valid in our graph, so our range is going to be all real numbers. Looking at our parent graph compared to our new graph, you can see that it has been compressed vertically, so it looks like it's been stepped on almost, and it's also been shifted 2 units to the right. So for your assignment, I want you to complete these 3 problems using the same process that we used above. Feel free to email me with any questions. These are going to be due by tomorrow night at 11:59.